Dr. Cristian Tomasetti obtuvo su título en Ciencias de la Universidad Trieste. Posteriormente continuó con su doctorado en Matemáticas Aplicadas en la Universidad de Maryland, además de realizar un postdoctorado en Bioestadística de la Universidad de Harvard y el Instituto de Cáncer Dana-Farber. Su línea de investigación se basa en definir la contribución de las mutaciones aleatorias y el ambiente en la etiología del cáncer. Su trabajo sugiere una baja contribución del ambiente en el origen del cáncer en la mayoría de los diferentes tipos de cáncer, dotando de una mayor relevancia a las mutaciones aleatorias. El Dr. Tomasetti ha publicado más de 20 artículos de resultados de investigación original. Actualmente es el investigador principal en el Hospital Johns Hopkins. Recibámoslo con un fuerte aplauso.
Buenos días. Estoy muy contento de estar aquí. Voy a comenzar, or at least I wish I could speak in Spanish and give you my talk in Spanish. Let me just thank, first of all, Luis for inviting me, and this place is beautiful. Beautiful people, incredible food, which is important to me as Italian. Okay, so let's start. So what is cancer and what causes cancer? This is a fundamental question, and this standard classic paradigm, even today, I would say, is that cancer is a mixture of factors that cause it, and those factors are environmental and inherited. And you can go and check on any major website of any major organization, and you will see that, here are some typical examples, you will see a long list of things that are typically lifestyle factors like smoking or diet and alcohol, sun exposure, and then other carcinogens and viruses, and so on. And then, of course, there is also the genetic or inherited component. Now, those are maybe websites for the general public, but we can go and say, look at the NCI website, and this actually is end of 2014. It has changed now. But if you look for causes of cancer, again, you will see a long list of chemical environments, of things that we find in our food, things that we inherited, and hormones, and viruses, radiation, tobacco, of course, weight, and so on. So this is how we understand cancer etiology, and this is how it's presented. However, a beautiful sentence, this was recently said by Nobel Prize Michael Bishop, is the following, and I'll quote it. "The work of what causes cancer is the most difficult form of cancer research at the moment. We don't know the cause of most of the major killers. We don't know what causes them the way we know that if you stop smoking cigarettes, you can reduce your risk of lung cancer." Now, this was also in a video, a series, or a documentary by Ken Burns, and when Michael Bishop says this, you can see this crab. I didn't copy it because I don't want to infringe copyrights, but you see this crab representing cancer, of which the 60% of it, it's hidden. You don't see it. And that symbolically to mean that for about 60% of cancer cases, we don't really know what is that causes them. So I'm a mathematician, and we say that this is a situation where there are two mutually exclusive alternatives. So either it's just that we still have to find those environmental and inherited factors, and sorry, for the rest of the presentation, I'll always call, or I may call environmental factors as E factors, just to be shorter, and H factor for inherited factors. Or the second alternative is that something major is missing from our current picture. In some previous work in 2013, we had shown that when you look at a cancer, so you sequence the tissue of a cancer patient and you find many mutations, and when you look at them, actually a large fraction, in fact, more than half of those mutations, were present even before the cancer started. And that was somewhat of a surprising finding, because in general, people thought that the great majority of the mutations were due to the cancer, the carcinogenic process. So this provided a hint, an initial hint, for this question that I wanted to investigate further. And so if you want to understand the signal of something, you also have to understand the noise that you're dealing with. And what is the noise in the situation? The noise is what I'm calling here R, which is the random replicative mutations. So these are random errors. They are made by normal cells where they normally divide by normal polymerases. And you can think about the example of a typewriter. No matter how good someone is, because we are humans, once in a while we are going to make a mistake. It's just the way it is. Our bodies work that way too. Now, on top of that, and I put a timeline at the bottom right of the slide, so you can imagine time going forward, and we accumulate these R mutations. They are kind of unavoidable, just part of the normal process of cell division. So this is a normal mutational process, on top of which we can accumulate the effect of, say, environmental factors. So these are the little E dots, mutations that are represented there. Of course, someone may be born with an inherited mutation too, which is in blue. And so what is important though to understand is that these R mutations, so these replicative mutations that are random, are independent of E and H. They occur no matter what. We can only make things worse by adding to it. And of course, there may be some lifestyle behaviors that may help reducing it. That's, that will require further studies. But so we have this normal process of accumulation of mutations. And there is a very large experimental evidence for this. In fact, there are pretty good estimates of what is this mutation rate in our tissues. And it's about, I would say, 3 mutations per cell division over the whole genome. And it's been estimated. Here I'm using one reference, but there are many. It fits also considering what has been done in previous analysis using cell lines. And there are many sources of these R mutations, and here I'm listing 4 major ones. So there are probabilistic quantum effects on base pairing. There are mistakes made by polymerases, and so on. So this is a well-known fact. So the fact is that there are 3 factors that contribute to mutations in cancer: environmental, E, inherited, H, and random replicative mutations, R. So the question that I asked at that time was, how much of the variation in cancer risk that we observe across tissues is explained by these R mutations? So how much is this noise before trying to understand the signal? And the thing is, it had never been measured. So this is what we did in this paper in 2015. And I'll give you the basic idea. It's actually very simple. It's a very simple idea. If there is a correlation between these random replicative mutations and cancer risk, then it should correlate in the following way. It should depend on how many cells I have in a tissue, because obviously the more cells I have in a tissue, the more opportunities to accumulate these mutations, and how frequently the cells divide. And so in this formula, which is only 1 or 2 very simple formulas I put there, you have this S for the number of stem cells the organ has, and D, which is the number of divisions in the stem cell lineage. And of course, these are, as you will see, these are estimates. There is noise in those estimates, and we accounted also for all of that. And now, the second part of the idea was that if I focus on one tissue at a time, I have the problem that, for example, if I look at lung cancer, there is going to be an important component of the mutations induced by smoking. So a way to, in mathematics we say average out those effects, is to put many, many tissues together. In that way, smoking may be important for lung cancer, but won't be present in some other tissues and so on. It's not a perfect approach by any means, but this was what I thought was a first attempt to address that question. And so here's what we found. Let me just go over the figure 1 second. So on the x-axis, we have the total number of stem cell division in the lifetime of a tissue, which is what I discussed before. And on the y-axis is the lifetime risk for that tissue. And so here we have more than 30 tissues. Each tissue is represented by a dot. And the x-coordinate is the number of stem cell division in that tissue, and the y-coordinate is the lifetime risk of cancer in that tissue. And as you can see, what we found was a very striking correlation, 0.8, and across tissue. It was, there is a clear relationship between how often a tissue divides and how many stem cells that tissue has, and how much risk you have in that tissue. Now, this helps explaining why, for example, colorectal cancer is much more common than, say, osteosarcoma, bone cancer. It's at least part of the reason, because a 0.8 correlation, it's not 100%, but at least an important part of the reason is that in our bones, we don't have as many stem cells, and the division rate is much lower than in colon, where, say, for example, the epithelial lining of the colon self-renews about every 4 or 5 days. So it's very high. Now, this is not a perfect picture. As I said, it's a 0.8 correlation. It's not 100%. And you can see below, there is small intestine, which doesn't have a lot less stem cells and divisions than colon, but its lifetime risk, it's much smaller. So this is not wanting to explain everything, of course. This is just attempted to give a first answer, and this is, in fact, a very, very strong correlation. So this is definitely part of the answer. Now, you may think, well, isn't this kind of obvious that the more cells we have and the more they divide, the more we have, we get cancer in a given tissue? And actually, the answer is no, it wasn't at all. Here, I'm just mentioning one paper that was actually the report of IRC workshop. So, many scientists working together and many different papers. And in this workshop, they concluded, and here I'm quoting, the tissues with a high rate of cell proliferation do not have a higher risk of developing cancer. Thus, no simple relationship exists between cell proliferation and carcinogenesis. So actually, it really wasn't clear at all. And there were some mistakes, but for time issues, I won't go over that. So going back to the figure, so the fact that we have a 0.8 correlation statistically means that the variation in risk, which means this variation from those cancers that have a very high risk to the ones that have a very low risk. So that variation, it's explained by the total number of stem cell divisions for 65% of it. Okay, that's what statistically this means. This implies, since at every single division there is a given probability of an R mutation, this automatically implies that R mutations can explain 65%, so 2/3 of the variation in cancer risk across tissues. Now, just to be clear, this doesn't say, some media interpreted this as if we were saying that 2/3 of cancer cases were due to R mutations, and that's absolutely not the case. Here I have a slide that hopefully can clarify that. So let's say we are considering the ocean death, and we say study the position of the moon with respect to the Earth, and we discover that the depth of the ocean varies, of course, and it's strongly correlated or perfectly correlated with the position of the moon. And this causes the high tide and the low tide. So the variation in the ocean, in the depth ocean of the ocean, is what you see indicated by the red arrow. Okay, so that's the variation that the moon can explain. The position of the moon does not explain the full ocean depth. Okay, so in the same way, we explain why some tissues have a lot more cancer than other tissues. We don't explain cancer, you know, the whole depth of what cancer is, of course. Okay, so, but of course, when you see such a strong correlation, this is a hint that maybe, as I said at the beginning, something major was missing from our general picture of what cancer etiology is. Now, when this result came out in 2015, IARC released a statement. It was published as a letter in Science too, where it was stated that if international rates were to be considered, essentially the results would be different, okay? And the fact that we chose the US population, if we chose a different population, the result would have been significantly different. Now, of course, this, you know, mathematically, it's a 100% correct statement. There is nothing wrong with the statement. Why? Because if I change the data that I'm considering, of course, the numbers won't be exactly the same. So this is absolutely true. But the true question, and I think what IRC was actually really going for, was, you know, are they significantly different? So is the correlation instead of 0.8, 0.3, or 0.4 in some other countries? And so this is what, this is based, and I'm interpreting here their thinking, but I think that what was thought is that when you look at the cancer incidence, and here is depicted the cancer incidence for all cancer types combined across all countries for which there is data, and with dark blue being the highest rate. So, you know, it's a well-known fact that there are differences among countries in cancer incidence, and so that is why the thinking was, well, if we change country where, say, some cancers are more frequent and others are more rare, then the results would be significantly different. So what we did is we actually took their database. It's found online at Globocan, and there are more than 400 cancer registries in 69 countries, representing about 5 billion people, so the great majority of the world population. And essentially, I repeated the same analysis for each of those countries. And so this is one of the things that was published this year, in 2017. And the result was actually, again, somewhat surprising. The result was that when you look at overall the correlation, it's again 0.8. And in fact, even when you consider the variation across all countries of the world, the full spectrum, it's within the confidence interval that we provided 2 years ago in our previous study. So essentially, this means that, from a statistical point of view, there is absolutely no difference, at least overall. Now, of course, there are some, as you can see, for example, in Latin America, the correlation is 0.73, so it's not as high as North America. But again, we have also countries like, say, Australia, where the correlation is, in fact, higher than the United States. So, so this is, again, a depiction of the same result, just as a figure, where the correlation, it's on the x-axis, and the number of countries that have that correlation is on the y-axis. So as you can see, it's quite concentrated around 0.8. Now, an important thing to notice is that there seems to be definitely a difference between countries that have high quality data and in their registries and other countries. And in fact, if you look at, and this is again, this is data on the left side, this is data provided by IARC for each country, and I guess we talked yesterday a little bit about cancer registries. For each country, and here is just a little piece, a little part of that list, IRC provides a score of how good the data coming from that registry is, with letters that go from A to G. And now, if you take the map that I showed you before, that's the one on top. I changed colors, sorry. Instead of blue, I made it, going from yellow to red. The top one is exactly the same map that I showed you before, okay? And the second map, right below, it's the data quality. So I only looked at the score, which I just described, provided by IRC, and I'm showing you what the data quality is in those same countries. And now, when you statistically adjust for the data quality, then the third map is what you actually observe. Now, this is just a statistical analysis. It's not that I completely trust it, but it's to make the point that at least part of the large variation that is observed among countries in cancer risk are simply due to differences in data quality. Okay, so now, when that paper came out, many asked me the following question. Okay, you are talking about variation, and variation is kind of a difficult concept. Can you give us a sense of how much you think these random mutations contribute to cancer in the sense of cancer cases? And that's it's an impossible question to answer. The reason is that cancer is a multifactorial disease. We know that. There are environmental factor, inherited factor, and these random mutations, they often work together. And unfortunately, the current epidemiological methods have a big limitation in trying to assess this type of questions. Let me give you a very simple example. So let's say we consider a smoker that get lung cancer. And let's say that this smoker got lung cancer by being hit in 3 key driver genes, okay? And these are the 3 dots represented there. And let's say that the smoking, let's say we were able to look at the genome and determine what caused what, which is something we still cannot do today. And let's say we were able to figure out that the first mutation was caused by smoking, and that the second mutation was caused by radiation, and the third mutation was just due to R. Then, from an epidemiological point of view, 100%, and let's say we have a population of clones, all with this situation, okay? Then 100% of the cancer cases will be attributable to smoking. Why is that? Because if I took away just the one driver mutation caused by smoking, and if, say, cancer requires to have at least 3 driver gene mutations to get, where it needs to get, then you wouldn't have cancer, right? So essentially, by removing smoking, I would avoid cancer. So that's epidemiologically what is defined as attributable risk. So 100% is attributable to smoking. But in the same way, 100% of the risk is attributable to radiation, and 100% of the risk is attributable to R mutations. So you see, this is the problem. So I thought it was possible to ask a better question, a bit more focused, which is the following. If I look at the mutation, is there a way to attribute those mutations to the different factors? Okay, that's something that maybe we can do. So we cannot say what caused a cancer case, but we can maybe try to probabilistically, at least in the population, determine how much each factor contributed to those mutations. So there is some math, which I always know I shouldn't put on the slides. So let me give you the idea. It's very simple. So let's say that we have this magic tool that was able, when we sequence a patient, I mean, this would be fantastic, right? And one day I think we'll be there. But so you have the timeline, and you observe, what happened, which mutations occurred, and you can even, they come labeled, okay? They have the label, they tell you what they are. Okay, this would be perfect because it would be then very easy to answer the question I just posed, right? I could determine out of all those mutations, I would look at the driver mutations and I would determine which factor caused what. Unfortunately, the reality still today is this one, right? They don't come with labels. There are still a few problems in sequencing data, and more than a few. But there is something that's very simple that I think everyone will agree with me. So let's say that we consider many, many smokers and many, many never smokers in lung cancer. And let's say we discover that, to make it simple, I'll make a deterministic statement. Let's say that the average smoker has 3 times more mutation than the average non-smoker. In fact, let's say for simplicity that every smoker had 3 times more mutation than every never smoker. And then if someone came to me, a smoker with lung cancer, and told me, can you tell me what is the proportion of the mutation that caused my cancer that was due to smoking? I think that even my daughter actually could answer that question. It would say, yeah, 2/3 of your mutations, on average at least, were due to the fact that you were smoking. So this is essentially the idea that was used in this paper to assess and attribute the proportion of mutations due to the various factors. And here, this is a previous paper. For example, it's known that in smoking, there is at least a factor, a 3 times higher mutation rate than in non-smokers. Here you can see the distribution of the mutation rate. In blue is the never smokers, and in red the smokers. And so when you do this analysis, using sequencing data and clinical information, of course, then what we were able to determine is the following. Let me explain this picture. Here, every patient is one body there, represented with 3 dots. Those are representing the key driver genes that were required to take that person to cancer. It doesn't have to be 3. The results is completely independent of how many driver mutations were required, okay? It's just a matter of proportions. But for simplicity, I'm using 3. And the patients that are surrounded by a cloud are patients that had some environmental factor affecting their mutational, their life. And the blue dots are hereditary mutations, the yellow are R, and environmental are gray here. So when you look at this picture, it is clear that, and this is for lung cancer, that you could prevent essentially 90% of lung cancer cases, this is a well-known fact, by eliminating smoking. As you can see, if you took the cloud away from each one of those patients, then none of those patients will have gray, environmental mutations. And so only about 11% are unpreventable. However, when you look at the proportion of the mutations, still about 1/3 of the mutations across the whole population is due to R, which is not a small, insignificant amount. Now, if you do the same thing in pancreatic cancer, where the proportion of preventable cases is much smaller, it's about estimated to be about 37%, and so 63 is unpreventable, the proportion that we estimated to be attributable to R mutation is much higher, it's 77%. And so you can do this for many tissues. Here I have again, I'm showing the case for lung cancer with the numbers for lung cancer. You can consider brain cancer, where it's estimated to be essentially all due to R mutations. And so when you put these numbers together, you get the following picture, which is that, and this is across 32 tissues, which include all main cancer types, breast, prostate, lungs, and so on. We can estimate that about 5% of the mutations were due to hereditary factors, about 30% due to environmental factors, and 2/3 due to our mutations. And this to us was very striking. Now, that analysis is based on current epidemiological evidence. There is a very important question, which we assessed in the paper, which is the following. What if there are factors out there that we still don't know of, and they have important effects on the mutation rate? And so the numbers I just gave you would definitely be wrong, would be overestimates. Our mutation wouldn't be as much as I just told you. However, it's very easy to mathematically show that even in a population where essentially 90% of cancer cases are preventable, about 40% of the mutation on average will still be due to R. And so we think this is a lower bound for how important is this component from a mutational point of view. So in this analysis, we really don't think it can possibly be less than 40%. To make maybe another example that's even more intuitive and doesn't require any math really, is let's say that we assume that the whole population is smoking, a heavy smoker, so we have this 3 times higher mutation rate than normal. Then 2/3, and this is true for every single person. I think the majority of the epidemiologists would agree that that's an extreme scenario, okay, to assume that we are all smoking pretty heavily. Well, even with that increase in mutation rate, the estimate would say that still 33, right? 2/3 would be due to smoking and 1/3 would be due to R. So now here, to show you something that it's in preparation, but I think it's interesting. I have plotted, so here we have TCGA data. These are sequencing data of cancer patients. Each color, it's a different cancer type. I know that you cannot tell which color, which tissue it is. Doesn't matter. The point is, you can, based on how often a tissue divides and what is the background mutation rate, I can estimate what is the mutation frequency that I expect to find in a given tissue of a given age. It's actually a very relatively easy exercise. So I can predict a certain mutation frequency. And then through TCGA and sequencing data, I can look at what actually was that frequency. And so here, each point is a patient with a given cancer type and with the predicted mutational frequency and the observed one. Now, I don't care so much to talk about the fit, how good is the prediction versus the observed. You know, this actually, it's an analysis that's very sensitive to, you know, what is the background mutation rate. So I don't trust it. But one thing that's very important is, if you look at the plot and you look at which of the tissues are the one with the highest mutational frequency, not surprisingly, what you find is, you know, the red cloud, which is melanoma, and of course there is a spread. It's not for every patient the same, but it's melanoma and lung cancer patients. Okay, so even though we don't know all the environmental factors that are affecting the mutation rate, we do have the observed mutational frequency. We can look at those, right? And even if we don't know what those unknown factors are, if they have an effect, that effect is measured by the observed mutational frequency. So whatever we see in the observed, it's reality, right? And at least to me, what this picture indicates is that we have discovered the large, you know, the most important environmental factors that affect, you know, the mutation frequency in our tissues, and we don't see anything like that that's going to be discovered in the future. If you look at the pink, there are a few on the extreme right. The majority of those pink patients, that's colorectal cancer. There are a few that are very high, and those are the ones that have mismatch repair issues. Okay, so anyway, that's why I'm saying the case of smoking and the 40% as a lower bound, I believe it's actually very solid. So we just published further evidence with respect to this type of results just recently in Nature. Okay, so I promised something else in the title, which was, so, from 2015, the first paper, to 2017, one great thing is that I feel that many more people now agree with this result. But now the question is, okay, let's say the R is very important on the mutational side, but we all know that cancer is not just mutations. So how much of cancer is mutations, right? And again, we are back to something that's in a sense an impossible question, right? But here is something in preparation that I want to show you that attempts to give at least a partial answer to that question. So, and this is my last equation, and it's very simple. So let's consider cancer risk. And let's think about everything that goes into causing that risk in a tissue and in a patient. So there are really two things. Mathematically, I can split them in that way. One is the mutation rate. And so there I wrote F1 of the mutation rate, meaning there is some function, I may not know it, but there is some function of the mutation rate. And so the higher the mutation rate, the more cancer risk, the higher should be my cancer risk. And then there is a function of what I call everything else, which means everything from the effect of the immune system, the microenvironment, and epigenetic, anything that you can think of, right? So that is definitely a true statement. So now I can play a game. I can, of course, if cancer is caused by R mutations, well, then that's a cause. I don't need to answer to that. But for example, what about smoking? What about obesity? What about viruses? What is that they do? Why is cancer occurring? Is it through the mutation rate? Is it through a combination mutation rate, immune system? What is it? And so the idea is that if I can estimate by how much some factor like smoking increases the mutation rate, and we have estimates actually for the effect of the mutation rate on cancer risk, then I can, and I know by how much cancer risk goes up, say in smokers, we have very large epidemiological studies that can tell us that. Then essentially, that would tell me how important was everything else. And here is, and again, this is in preparation, and these numbers are not final, but here are some examples. So for smoking, and you see the tissues on the left, LUAD is lung cancer, lung adenocarcinoma, there is skin cancer, oral, head and neck, bladder, and liver. MR is the increase in mutation rate that has been estimated in this newest data set to be due to that environmental factor. And then there is the prediction of how much just the fact that mutation rate goes up should cause as an increase in cancer risk. And in the last column, what is the actual observed increase in cancer risk, okay? So as you can see, in general, for smoking, it looks like the main effect of smoking is through increasing the mutation rate. Because in fact, overall, the increase in mutation rate, it's enough to explain the increase in cancer risk, okay? Similarly, I've looked at obesity, and there it's interesting because it's a little bit more of a mixed picture, at least based on what we have right now. We'll see if it's confirmed. But so let's see, we have kidney, we have uterine cancer, again liver, and esophageal carcinoma. And there, as you can see, if you look at compare the predicted to the observed, again, in many cases, the effect seems to go through the mutation rate. So we observe mutation rates that are enough to explain the increasing risk. But we have also the case of uterine cancer, where there is no significant increasing mutation rate observed when you sequence and compare obese versus non-obese people, cancer patients. And so that says that the effect of obesity in causing an increase in, I mean, it increases uterine cancer by, the odds ratio is 7.1, so it's a relatively high increase. So that seems to say that something else is happening. Obesity is doing something else that's not through the mutation rate. So I think this is an interesting observation. Okay, so in conclusion for this part, I believe that this analysis showed that R plays a major role in cancer mutation and in fact in cancer. Now, I wanted to address this question, right? So what? You know, I get this actually very often, right? So they say, okay, great, so what? You know, I mean, you know, you can stop smoking and, you know, but so what can you do? You know, what does it mean? You know, what is this adding to the picture we had before? And let me tell you my answer to that question, because in fact, this is, to me, a more annoying question that, you know, say someone that's scientifically trying to argue with the results. And here is my answer. So first, I just remind you of what we read before from Michael Bishop. I think it's always important to understand a process, right? So the added knowledge, it's, in my opinion, essential. So even just for that, I think it would be an important thing to consider. Now, but there are very important implications for cancer patients, right? Let's say if I were a cancer patient in 2014, and in fact, I can tell you I received many, many emails of professors of hematology of various well-known universities who had, say, for example, their child getting childhood leukemia, and writing to me saying, when I saw the abstract of your paper, I cried, because when your son is detected with childhood leukemia, you immediately think what I did, right? And why is that? Because, again, if you went online and say, okay, why this happened to me, right? The answer was, you must have done something wrong with your behavior, or you inherited something wrong, okay? Essentially, there was almost no mention, actually no mention there, of this third possibility. So, in fact, I'm very pleased that the most, you know, I would say, well, definitely one of the most important resources of information today, which is Wikipedia. I use it a lot. Now states in the second paragraph, it's actually now, it's the, please don't change it. I didn't write it like that. Someone went and did that. You know, now it says, after listing environmental factor and you know, inherited factors, it says finally, okay, it's fine. Finally, random mistakes in normal DNA replications may result in cancer-causing mutations. Okay, I think this is progress with respect to what we had before. I think this is important for patients. Now, but that's not all. I think there are important consequences for cancer prevention and for research. And I'll talk in the last minutes that I have, I'll talk about that. So, you know, the way that the picture was before was focusing on keeping the enemy outside, okay? So you don't want to be obese, you don't want to stay in the sunlight for too long, you know, you want to avoid viruses, you don't want to smoke, all right? But as long as you protect yourself from these insults, right? It's like you just keep the enemy outside and you can control the occurrence of cancer. Unfortunately, that's not the complete picture. That's only part of the picture, okay? The problem is also internal. In fact, to be current with, you know, what is happening today, maybe this would be a more appropriate picture, right? So the truth is that it's also something that's just part of how our tissues work. And So I think it's very important to really, really let this thought, soak in our minds and think, what does this really imply for, future cancer prevention and research? And this problem is not going to go away. In fact, it's going to become more serious. I think Carlos already showed the slide yesterday. That was neat that we had the same slide. Again, from The Economist, right? The world population is aging. This is a very well-known fact. We also all know that the effect of the mutations that we accumulate in life, the effect is exponential, right? And so this problem is not going to go away. So here is, what I think. One important thing is that, of course, we want to do primary prevention. It would be crazy to think that that is not important. The effects of smoking and everything else, it's so evident. I mean, those are among the greatest results in cancer research. But, to deal with this other component, secondary prevention becomes extremely important too. And in particular, I'll talk a little bit about early detection and what I've been focusing and working on. So by using liquid biopsies. So let me describe first a specific case. So let's look at pancreatic cancer. And these are data for the United States. So when you look at pancreatic cancer, the majority of the patients are diagnosed at late stages, okay? If you, localized is only 10% of the patients. And even when you consider localized and regional together, it's still only about 43% of the cases. So the majority of the patients are detected late, and it's a very well-known fact. And now on the right side, consider the 5-year survival of those patients, okay? To say extremely poor, it's still an understatement, okay? We are talking about something that goes from 3 to 5% survival. And so, what do you do? So I'm lucky that Dr. Vogelstein is essentially, our offices are very close, and this is something that has been working for many, many years. And they have developed techniques to do sequencing using liquid biopsies, like plasma. And I guess he needed, you get this data, but then you have to make a call. Is this a cancer or this is a normal person? And so again, it's an issue of understanding what is the signal, the noise and the signal, right? And so I'm in charge of the bioinformatics side of these projects. And these are very large projects. We are going to sequence 50,000 people in the next 2 years, healthy women. So, but here is a paper that we just published a few weeks ago, and it's one example of what can be done using liquid biopsies. And so, and here is the data. So, as you can see, let me tell you, just give you a few facts about it. So we had 221 PDAC patients and 181 normals to use as controls. These are actually relatively large numbers. And what we ended up doing, and that was kind of like the novelty, maybe I should have mentioned it there, of what done in this paper, is that we combined mutational information with protein information, and it worked better. And so, as you can see here, are depicted the sensitivities. The overall sensitivity is 64%. And by the way, this, as you can see from the plot, we only consider patients in stage 1 and 2. Okay, so these are the ones with the 3 to 5% 5 years overall survival. And as you can see, overall, we can detect cancer, cold cancer, 64% of those patients. which I think is very exciting, or at least I'm very excited about it. And with a very high specificity, 99.5%, because of course you don't want to tell a person you have cancer and then that's not true, right? And there, the mutation and the protein information is listed. Okay, so in conclusion, I think I provided some evidence. The third factor, which I call R, plays a major role in cancer mutations, and this contribution has been measured. The method is not perfect, but I believe the numbers are in the right ballpark. These results provide relief for some patients, and there are important implications for cancer research. And in fact, I think there should be an increased effort on early detection and intervention. And let me thank my collaboration with Dr. Vogelstein and my PhD student, Lou Lee. Thank you.